All right, so let's get started. So the you got kidding. It's not my it's not technology. It's availability of chalk. There we go. All right, so so a couple things before we get started. So there's only about 5 classes left, right? I think it's 5. What's that? No way. 5 classes left. So, and I'd like to at least leave 1 class for an exam review. My plan for the remaining classes, just so you guys know, and I was able to somehow, hopefully you guys got the message on Blackboard or CUNY First that I sent out with the videos that you should watch before classes. But by today, I'd hope that you guys had watched my amine videos. Obviously, went over amines a bit last class. I'm going to spend today finishing up on amines. Then I'm going to spend 2 days on CC bond forming reactions. So before Wednesday, make sure that you watch the video that I've sort of put up there on CC bond forming reactions. That's 3 of the 5 remaining classes. And I already told you guys that I want to spend 1 class on sort of exam review. So basically what that means is that, yeah. Yes. So we'll get to that in a second. So the quiz will be on amines and CC bond forming coupling. So now that means 1 more day, and in that day I will provide a sort of a broad survey of the material on lipids, carbohydrates, and polymers. Basically what that means is I'll probably spend about 20 minutes on each, just giving you guys a general view on each of these. Certainly polymers is based upon chemistry that you guys have already seen. So I think that we can do that. So what I'll do is I'll put up some previous videos where we do discuss a little bit of them, but the emphasis in your remaining time here should be on amines, CC bond forming, and again, sort of more general broad knowledge of lipids, carbohydrates, and polymers. And so I don't think that you're going to have to put too much emphasis on those. But there it is. Okay, so at the end of last class, we discussed sort of amines, and we began to introduce amines. I hopefully tried to give a perspective on them comparable to alcohols, right? So alcohols can be nucleophilic, they can be converted into electrophiles as well, and in many ways amines are similar in that extent. And so much of last class was spent with a focus on amines as nucleophiles, right? So all of the amine reactions that we saw previously were about how do we make amines, sort of primary, secondary, tertiary. Each of these dealt with sort of the nitrogen lone pairs serving as nucleophiles. And then sort of towards the end, we sort of discussed how you can take an amine, right, and specifically a primary amine, and how we can actually turn it into a nitrogen-based leaving group, right? So, and the way in which we did that, right, was basically HONO, or HNO2, right? So we know that if we take a primary amine, hopefully you guys all went through this mechanism, basically use HNO2. Sometimes it's sort of the sodium salt of that with acid, as I think your book sort of describes. And what you end up getting, we went over this a little bit yesterday, there's going to be a counter ion based depending upon what you sort of have used here. So usually there's just an X minus based upon the reagent that you have. But this is sort of I guess the best way to describe this is the mother of all leaving groups, for a number of reasons, right? If you guys recall, when we start discussing things like sodium hydride, we don't necessarily even have like a pKa tube, but you're sort of generating hydrogen gas, and that drives the reaction. As you can imagine, in this case, what ends up happening, right, is your leaving group is nitrogen, right? And so at least from a sort of more SN1, or E1 type transformation, if you're just going to have the leaving group leave, right, we end up having nitrogen as your leaving group. Nitrogen is ultimately going to be a gas, okay? What this means, in essence, is that nitrogen, I guess the sort of take-home lesson, with nitrogen, we'll go through a couple examples of this, is that the nitrogen leaving group ends up disobeying a lot of the rules that we've seen previously. There's a lot of chemistry that you can do with nitrogen as a leaving group that we might not necessarily want to do with things like halogens or so forth, in large part because of this sort of drive of a loss of nitrogen, rendering it reactant. And so one of the transformations that you see, so I'm sort of going off the cuff here to give you sort of one example. I'm trying to remember the specifics of the reagent, but it was something like this. So here's a carboxylic acid with a leaving group. This is sort of my little, I don't know if I told you guys my benzene story, but this is a precursor to benzene that's sometimes used. So you guys learned about benzene within sort of nucleophilic substitution, so you treat it with a really strong base under a lot of high pressure and so forth. This is a much more quote-unquote gentle is, I guess, the best word that I can use for it. This is a highly explosive compound, in large part because when you have an explosion, right, what you're generally going from is a solid to a lot of a gas. And as you sort of look at this molecule, when you treat it to a base, right, what you end up getting to is a carboxylate, and I forget the exact details, but this is always something interesting to talk about, because I think it, again, highlights how strong of a leaving group nitrogen is. When you make this intermediate, what this will do is you notice that you can generate two gases fairly readily, right? One of the gases is CO2, right? And the other gas is nitrogen. And so you lose CO2, gas, nitrogen, gas, and the net result of that, depending on how you want to push the electrons, right, as I sort of drew, is sort of benzene now, as I've sort of drawn it in the sort of ionic state, but again, that's sort of benzene. And when I was doing my postdoc, actually one of the very first, I don't know if I told you guys the story, but whatever, I'll tell it because it's my one little rendezvous with benzene chemistry. And I had a salt that was something of this nature, and we were trying to do this reaction with benzene. And it's rare that I've been in a situation in a lab where I've been like setting up a reaction and sweating because I've been so scared. And so this was one of those cases. You sort of set the reaction up, it's behind this blast shield. I had these thick gloves on in case it exploded so it wouldn't destroy my hands. And so I'm sitting there trying to sort of set up this reaction. And I set it up, I got it to work. The actual reaction I was looking to do didn't work, but I certainly at least got the benzene to work, and then it did some other chemistry. And at the end of the reaction, like anything, you sort of take care of it at the end. You sort of quench it. You make sure that it's no longer something that's going to be dangerous. But one of the things that I had sort of forgotten is I had I forgot if I weighed it out or what, but I had a little bit of this stuff on a spatula. And you have to use like special spatulas. You can't even use like metal spatulas. You have to use like Teflon coated spatulas because even the metals that are associated with that could sort of catalyze this process. But through the course, I got a little bit, just a tiny bit, probably a half a mig on my bench top. And I didn't know what it was, and I was cleaning up, and I was like, what is this? And it wasn't coming off with standard stuff, so I went and scraped it. And I was like, pop, like really loud. Not really loud. It sounded more like one of those poppers that people used to throw. Just a tiny, tiny bit. And so I had a little, again, it wasn't a super explosion. It was nothing dangerous at that point, but it was enough that it was like, wow, this stuff, you can imagine on a bigger scale. There's a reason that I was sweating when I was working with this stuff. So anyway, so that's just an example of nitrogen as a leaving group. And I think with a little story that might maybe drill it home a little bit more. But certainly when we start talking about nitrogen more generally, one of the things that you'll see in your book is you'll see a whole bunch, and in the video that I posted, I won't go into too much depth on this, but I just sort of want to make this sort of broader point, is that, you know, in the previous nucleophilic aromatic substitution chemistry that we discussed, right, there was really two types of nucleophilic aromatic substitution, right? There was the one where we had some type of sort of resonance-based leaving group. So again, this is the nitro version of this, was the one that we saw in our book. I just sort of generalized this right here, but again, there's the nucleophilic aromatic substitution, whereby you can push the electrons up into the system, right? And so the chemistry of this is consistent with, say, for example, addition into an alpha-beta unsaturated carbonyl, or of this sort of nature. Bless you. Right? So you get to sort of intermediate, and then this is how you ultimately exchange through. But this is you notice that the attack of this takes place in large part because you can sort of delocalize the electrons throughout the aromatic system, ultimately up onto the group up here. You can directly do this as well, if you remember. Again, getting back to benzene, if you don't have anything up at that position, you can also take this and treat it with a nucleophile as well. But again, this requires substantial heat, right? So say, for example, sodium hydroxide or something like that under very, very high heat. So we're talking about 200 degrees, you know, super, super high temperatures. You can get that displacement, but again, it takes place through, right? First elimination of benzene. Space here. For this, hopefully, this is just a review. This should look familiar. You guys should all be able to draw the mechanism of that, right? You sort of get this elimination to generate benzene, which is then attacked by the sodium hydroxide and subsequently deprotonated, or protonated, I should say, once you have the anion there. But again, this other one requires a significant amount of heat. If you read through your book will discuss a variety of different ways in which case once you generate this nitrogen as your sort of leaving group, you don't need these extremes, right? This is such a good leaving group that you can just make it and you can sort of treat it with various nucleophiles and it will simply displace this. Saul, did you have your hand up? Okay. So again, much easier. And so, you know, if you have this group here, you can certainly treat it to just sort of generalize it as nucleophile, and that's going to be much more likely to work. And again, one of the reasons for this is that nitrogen can serve as a leaving group. What is it that would not want us to attack this ordinarily? Well, one way you can imagine is through benzene, but you could also just sort of attack it more generally as having the nitrogen being a leaving group. And so in many ways, it may be considered maybe more SM1-like or so. But the other thing that you'll see with nitrogen leaving groups And the parallel that you can draw under, again, perhaps not as forcing conditions as we've seen previously, but if you guys remember, we'll sort of revisit this very quickly. Right, so maybe you guys see what I'm about to do here, right? If we take this molecule here, this is sort of a refresher, and we treat this to, say, acidic conditions, we can often get to rearrangements, right, that will ultimately form molecules such as, if I did this right, you get a molecule such as that one right there. Does this look familiar to you guys? If I did it right? I did, yeah. You guys remember this reaction from the very beginning of the semester? What else do you want to do? I'm liking that you're asking this question, but what's the alternative? So again, we've seen time and time again that carbonyls can be driving forces behind chemical reactions. There's a couple of questions that you could ask for this. One might be, what is the driving force of this transformation? But there are multiple other products that could form through this. And we can discuss those, but the question here is not, what about those others? If I'm telling you that this is a rearrangement that's taking place, whether or not, if we actually did this in a reaction flask or not, we could propose that other things would take place as well. But this is certainly a possibility that could take place through a pinnacle rearrangement, right? And so the mechanism of this transformation, as you guys remember, is that we would protonate this molecule. Again, this represents a somewhat more difficult, oops. Right, so we have water, right, so you guys remember the pinnacle, the water now leaves. God, this chalk is horrible right now. And what we have, right, is a system here where we now have a carbocation, and this is ultimately what drives the sort of rearrangement, right? So this is a rearrangement that we're sort of driving here, where we basically are going to break this bond that I'm showing you here. It's going to be a 1,2 alkyl shift. So once we generate this carbocation, there's this shift that can take place. The driving force in this shift, right, which is in general the driving force in much of the pinnacle rearrangement shifts, is the formation of the carbonyl. Ultimately, when we do this migration, right, what we're going to have is a carbocation adjacent to that alcohol, which can then obviously be stabilized, and so you can just sort of draw the resonance form and ultimately get to the pinnacle product. Now, just trying to make a broader point here to remind you guys of the pinnacle. I would say that an alternative question to this could be something about, I thought maybe where you were going, Anton, was what would happen if I instead made water here as the leaving group. Maybe that could be a good mechanism question for the exam. But if that ends up being your carbocation there, another product could form. And so I'm not going to go over it right now, but you should sort of, that was kind of what I was getting at, is that we had the water form here and form the carbocation there, which would ultimately lead to this catechol product, but that too would be a tertiary carbocation that could form, that would lead to a different alternative product. Which one of those would predominate in this reaction, I'm not quite sure, but that would be the alternative. But again, the reason why I'm bringing this up is that you notice something else about this reaction, right? And that is that the ability to form the carbocation becomes essential in Pinnacle. And so when we actually think about the name of the Pinnacle rearrangement, do you guys know what Pinnacle is? Anybody know what Pinnacle is? So Pinnacle is the reason it's called Pinnacle rearrangement. It's not something like a lot of times these are named after people. Pinnacle rearrangement is one that's actually not named after a person, as far as I know. Maybe it is, and in which case the molecule would also be named after that person. But Pinnacle is the sort of the standard molecule that you've seen there. So that is in fact Pinnacle. And you notice that what's substantial about being able to perform a Pinnacle rearrangement is that this rearrangement is in essence a carbocation rearrangement. It's comparable to what we have sort of learned, for example, when first semester chemistry, when you started learning about some of the byproducts that could take place in an E1 or an SN1 type reaction, right? The moment that you form a carbocation, you can begin to get skeletal rearrangements, but you need to be able to form that carbocation, right? And this is kind of the point that I'm ultimately going to try to make here, is one of the reasons why this would go, right, is that we have an intermediate that is in fact a tertiary carbocation. Sort of Anton was bringing up, that also causes issues here because you could also get an alternative tertiary carbocation up here, but both of those situations would be, again, tertiary carbocations, and so that's a sort of a more stable carbocation that you could ultimately access and potentially take place in this transformation. But what's interesting is that nitrogen, you begin to see nitrogen sort of ring expansion. So this would be an example of a ring expansion. You can in fact do similar transformations now on, for example, primary carbons. Okay, this is not something that you would ordinarily do if that was a diol and you tried to treat this to acid, right? So going back, let's actually go based upon what we were talking about earlier. So if I try to do the same ring expansion from this, right? If I was trying to do a similar situation here, if what I wanted to generate was, actually this is a good opportunity to sort of revisit this mechanism. So if you guys can all just sort of follow along with me and try and predict what mechanism would ultimately form here. If we were to want to do this transformation, right, what we would need to do is we need to protonate that guy right there. And so in order now for the Pinnacle to take place, right, we have to leave water, and the problem with that would be what? It's a primary carbocation. So this is not going to work. Instead, back to Anton, what is more likely to happen here? If we were to now predict what the product would form, because we are under acid, we've got two alcohols, what would happen if instead of protonating this alcohol, instead we protonated this alcohol? Let's go through and try and predict what the product of that transformation would be. Yeah, let's look. So I'll just do 2. So I'll go right to the carbocation. Hopefully you guys can all get to there. But Nicole just said a hydride shift. you guys think?
No, hydrogen shift could be the first. Like, you said it's not going to happen.
What's that?
Can we?
Well, once we're at this carbocation, right, you don't have those alkyl groups like we had there before, but I think what Nicole is sort of noticing is that we do have, again, what sort of drives a lot of these pinnacle type transformations, right, is the fact that you can sort of generate, there's a difference between a carbocation here and say a carbocation, that we had shown previously if it was here. What's the big difference between a carbocation there?
Stabilized by balance.
Yeah, is it even really a carbocation? Is that even really a carbocation? It sure looks like a carbocation here, but what is it really? Yeah, you got to consider the resonance structure. What it really is a carbenium. It's sort of an oxycarbenium, or however you want to sort of state it. But it's really the protonated aldehyde is really what you're generating here. You're really not generating the carbocation in principle. It's more likely that the major resonance form would be that aldehyde, and so you might predict instead that this would be the product that you would want. Yeah. And so the alternative here, right, in a transformation like this is that if we wanted to get this molecule, we need to be in a position where we can potentially generate a primary carbocation. And one of the ways that you can do this is instead having nitrogen as your leading group, and I'm going to take this opportunity to do a mini synthesis problem. Fine, I think we do. Right, and so now, and again, you guys should be able to go through that mechanism. You generate the primary carbocation. But I do want to use this opportunity that we have right now. We will do that. You guys should all be able to show a mechanism that shows that deprotonation at the end, ultimately. So if you maybe a little bit of base. Sorry, thank you, good catch. 7, yes. Yes, my bad. Thank you for that catch. So this would work. But I want to use this as an opportunity to maybe discuss something else. And rather than discuss this, which again you can read in your book and everything else like that, this might be a good opportunity to sort of maybe spend about 15 minutes doing a little bit of sort of revisiting synthesis. And this just sort of came up in my mind right now. We'll work through this as a group together. But, it's nice to be able to just take and draw a molecule on the board and say, oh, we'll just start with this instead. But what if what we had was that molecule right there? Right? So I want you guys to spend a little bit of time right now asking, if we have this, so let's give you guys a little bit of time to think about it, and then we'll go through it as a group. I don't have a clear answer in my head. I've got some general ideas. So I'm kind of curious to hear what you guys think of. But how will we convert this molecule into this molecule? And one of the keys off the bat, right, is what is one of the challenges that we often don't address that much right off the bat.
On this boat,
Yeah.
hydroxyl.
Yeah, is that I've given you guys two hydroxyls. So maybe to start you guys off, well, whatever, we'll see what you guys come up with. There's ways around it that's based upon the chemistry that you guys know. But spend a little bit of time on this, and then we'll go through it as a group. So how do we convert this diol to this? What's that? Oh, to me? It's possible. It's possible. Yeah, yeah, probably. Yeah. I don't know. It's unclear to me because the other thing is that never free to get.
I'll start like
I don't know which. Truthfully, if I set that reaction on it, but I don't know which one. Because the other counter to that is you're right that the third counter might be the 600. Exactly. But right. But one of the potential differences between the two is in the one case there's a specific. So but. Well, so yeah. I think your thinking is fine. I think you're probably right that probably would go the other. This doesn't necessarily lie into my long-term plan here to sort of address this other guy, but it could be a challenge.
you could do like
I don't know, but you're probably right. If anybody, I'm gonna give you guys maybe another 7 minutes or so, and then I'd like if somebody has something that they like, maybe you can show it to me, or go over. Even if you use some general ideas. You see this bunch of it's just such a good movie. Now, whether you're actually forming, whether we're actually forming a real carbocation, or whether it's just such a good movie group that it's sort of a more concerted process, I'm not sure. What's that?
probably nothing quick enough.
It might just be more. Yeah. So quick would be so quick that it's instantaneous, right? They will take place at the same time. So that would be considered a concerted process where the group is leaving as the bond is forming. But I think it's like sort of illustrating how good the leaving group is to this. Let's say you try this.
Basically,
And this is small enough, for example. So I like your thing. But it's staring so that would be another thing. And in fact, that's one of the reasons
oh, never mind. That's the other way. I was gonna say it's either both ones. You can get either 55
spaces.
or you can just not roll either surprise. Or if you just eliminate
and so
what if you just I mean, for a simple but then there's gonna be some errors.
and silent questions as well. People listen to
You can do it that way. No, I'm not doing retro. Because that's like a start. No, I am doing it now. I'm just not doing it retro. I'm just saying like that. Oh, you retro. It's just, like what I want. What's the pictures of the selected? That's really nice. Oh, it's too bulky. Maybe.
yeah.
That's the thing. I just didn't use the original do that so much with my one. I know, right? Just a little bit of that. What if you just
I mean, this is
propane goes away? You had a turpentine.
can you make the other
Yo, you just solved it. Wait. Wait. Yeah, because you have a perfect admin. There is such thing. Yeah, there is. Which chapter is it? This one. Yeah, you did. Yeah, right? It's all. Yeah, good job. Okay. I wish I had chapters. Show you. So it's right. That's right. So it's pretty much that.
Awesome. Awesome. I love it. I love it. I may want to. I love it. I love it. I love it. I love it. Where's this?
I think it's not sorry back.
Alright, so I'm seeing some good answers. I'm seeing a diverse range of answers. I'm seeing a lot of, what I'm really liking about this is I've seen about 4 or 5 different answers that are all, I really like. Yeah, you may want to, yeah, I think, well, this is the question I have here is just tell me how in the right ways, so we'll discuss that, but I think that's, you could, oh, that's not wrong, that's called orthogonal protection. You just gotta make sure that you can take off one in the presence of the other, and that one will survive, right? So that's orthogonal protection. So you learn about that. All right, so because I do want to get onto a few other things, I've seen a lot of really great answers to this, and I've seen 2 different strategies from people trying to, and maybe a third, that were trying to figure out how they would distinguish between one alcohol and another. And the one strategy, and actually it was equally split, the one strategy tried to play on the idea of sterics, right? And so a lot of people said if I treat this to, say, for example, a halogenating agent, or if I try to convert this into a leaving group, I might be able to get selectivity of this alcohol over this one because this is more sterically exposed. And this is a strategy that's actually used quite a bit. Now, I saw every single type of halogenation method. I saw PBr3 to make into a bromide. I saw SOCl2 to convert it into a chloride. I'm not necessarily sure that those are going to be the best in terms of selectivity, but I like the thinking nonetheless. And so I'm perfectly cool with either of those. I think the bulkiest leaving group that we could have would be something like even like a tosylate, right? So tosylate might be a little bit more sterically bulky, and there's some cool things that you can actually do with some of these where you can actually activate something like a tosylate. And this is done in silation chemistry as well. Where you use, I don't know if I think I discussed this maybe with TMS, with silo groups, but you can imagine getting away sometimes with, I'm pretty sure you can do this. So what's common is that you activate this with a Lewis base. So this isn't something we've discussed, but I figure I'll just sort of make a comment here because it is an activating agent that people often use to select for one over another. And what happens is this activates this and makes it an even better electrophile, but in doing so, it's one of these weird things where like, it's one of these weird instances with Lewis-based catalysis where it's more reactive and it's kinetically it will take place faster, but it catalyzes the process because then the subsequent reaction is faster. So people will often do this, so you basically throw this in there with this. But again, we didn't discuss this, but I thought it was, so I wasn't looking for this necessarily, but I thought I would show you guys this because we're discussing a situation where we're trying to decide between, try to drive this based upon sterics. And this obviously is a much more sterically bulky electrophile. Jessica, did you have your hand up?
Oh, I have a question about another way.
Yeah, so we'll go back to the other ones, but we'll complete this one as well, right? Now, from here, some leaving group, I'll just leave that as X because I was perfectly cool with any of them as long as you said, oh, sterically this is going to be bulkier than the other. So here I saw a few things. I saw a couple people say, well, let's take this and treat it with NH3, so that would be ammonia. What might be the problem with treating this with ammonia? Why would ammonia, we might get a little bit of product, but why would treating this with ammonia maybe not be the best nucleophile? What did we learn about in last class about trying to make primary amines from ammonias? I see Jessica's going. Keep going, right? So you might you might start getting the tertiary, you may just get a lot, it might just be messy, right? So ammonia is the nucleophile. While mechanistically that's a good one to use, and in principle it makes sense that it could work, sometimes it's challenging because you will get over alkylation. Maybe you would argue that this is much more sterically bulky, so maybe having a second addition might be trickier, but so maybe you have a little bit of better chance just because of the nature of this one. But we learned about other nucleophilic sources of nitrogen, right? And one in particular that we focused on, right? So one that we discussed in class. And what was that, Saul? What's that?
Oh, azide?
An azide, right? So the one that we learned of in class is an azide. So say, for example, Na, N3. And now we get to, now we get to the azide there. Now how do we convert the azide into the nitrogen leaving group? Yeah. HNO2, that's to take the amine, NH2. So we need to get that to the NH2 first. Yeah. Yeah. Yes, so we can reduce it down first. So H2 palladium, or Staudinger reduction, or maybe even LAH we might be able to get away with. That would get us to the amino alcohol. And now we do the, now we do the HNO2 to basically take the amine to the nitrogen leaving group as we saw previously. Yeah?
Would the H2 and palladium get rid of the OH?
So, would we get hydrogenolysis? I don't really think we often discuss hydrogenolysis too much, except in cases of, I don't really touch on it that much. Usually you'll see it with we did see it a little bit with benzyl alcohols and stuff like that. But so it might be a byproduct that you could get. So you might start to see this. We don't really touch on it that much. We only really touch on sort of hydrogenolysis for benzyl deprotections. And so I would just, for at least the sake of this course, I wouldn't worry about it for this case. Yeah?
Can I say that it won't go, the palladium won't touch the OH because it's sp3 microvac, and it's easier.
So it might be
to
more
go-
sterically bulky as well. But again, hydrogenolysis is, again, we've really only learned it with benzene, and you can draw different mechanisms of how, yeah, let's not worry about hydrogenolysis too much at this point. Jessica.
I guess two questions. And if we were worried about it, can we just protect it with TMSCL?
Bingo, sure.
And then to form the halo, whatever, the XOH species that we call, for the first step, could you do a base catalyzed dehydration and get a primary alkene? Or would that
Base
only-
catalyzed
So
dehydration.
sorry, acid catalyzed. Like, could you get an alkene, a primary alkene? Like-
Well, if we did that, then we'd have, wait,
And then
we
just
can't.
do HODR.
Well, we can't generate an alkene there because we then have 5 bonds to that carbon.
But,
You want to eliminate and have the alkene this way and lose the, and then you have an aldehyde. You'd eventually, I think the problem is you'd eventually start to get to some of these other, that would also be like you can get a similar mechanism that we saw of the aldehyde formation, you could also get through elimination, and then tautomerization would be another way that you could envision getting to that product. But I saw one other way, and then we'll move on to some of the other stuff, but I saw one other way that I really, really liked that a few people did. So this was playing on sterics. There was one other strategy that I really liked. One person was bringing up orthogonal protecting groups, so protect this with something, then protect this with something else, then remove this. You know what I mean? So you could do that as well. But I just want to go with one other one because I thought it was really quite clever. And there's a few people that did this. Gavin, did you do this? All right. So Gavin, what did you think? Yeah. I thought this was really clever, and a few people did this. And that would be selective, right? Why would that be selective, right? You can't oxidize a tertiary alcohol, right? And then now that we have an aldehyde, now what can we treat this with that we might not have been able to treat it with previously? What's the next step, Gavin? Yeah, so we now do a reductive amidation. This is another way, this is one of the ways that we learned that we can make these, that we don't have to worry about the over reduction, so NH3 and sodium borohydride or sodium cyanoborohydride. I'll just put sodium borohydride because I like to keep it a little bit simpler. And then when they're there, then we can complete the synthesis as we did previously. And so, again, there was two strategies. I think that was really nice to see here, was that some people were looking at sterics. Other people noticed that, well, only one of these can oxidize because only one of these has a proton, and so maybe we can convert it to the aldehyde and then do a reductive amination. So, nice work, guys. I'm really happy with what I saw there, so keep it up. All right, so that's probably stop there for sort of nitrogen as a leaving group. But I want to discuss two additional, as was evidenced by the last exam, right? One of the things that I would like you guys to think is sort of a little bit of these advanced stereochemical concepts. And one of the things that we discussed, maybe at the beginning of the semester, is the nature of stereochemistry of elimination, right? So sort of just to refresh very quickly, right? If we were to have a molecule that looks something like this, say bromine, and then let's say, okay, so if I were to take this molecule and I were to do an SN2 elimination, right? And we assume that it goes through, for the sake of what we'll discuss here, we'll use a smaller base and assume that the stereochemistry that we get will go through Lyson's rule, right? Such that we will, or I guess sort of inverse of that, but we'll use a small base like sodium methoxide, right? And what we're going to get is one of two possible products. We can get that alkene that I've shown you there, or we can get that alkene there. Okay, so I guess what we would consider this is, I guess because this would take priority, we consider this sort of cis, we consider that trans. Okay, and so these are the two different alkene isomers of one another. Now let's all take a little bit of time right now and think about which of the stereoisomers we would generate and why. So everybody spend a little bit of time. If you think you know, you can come by and look. But spend a few minutes. And I don't think that this is necessarily something that you're going to be able to see. I don't think this is something you guys are going to be able to just see without drawing it. So what do we need to have happen in order for a sort of an SN2 elimination to take place? What's that? Yeah, so we need anticoplanar. As is drawn right now is this bromide anticoplanar to, so what we want is that to be anticoplanar to that hydrogen. Are they? No. So go ahead, you gotta try to draw it into a form that will allow you to see when it's anticoplanar, and that's the way that you would then do the stereochemistry. So I always say anti-periplanar, but we're saying the same thing, right? Basically. Okay, so again, this is going to take, you guys have to, maybe some of you can see this without having to redraw it, but I think it's a good habit to get into to try to draw it into this form. So I like seeing chemistry in the plane of the board. This is usually what I like to see, is it's just something that I like to do. So that's the anti-periplanar, anticoplanar relationship that we're talking about. And so one of the things that we want to sort of ask here is how would we rotate this molecule around such that, what is coming towards us here and what's going away from us here? So I don't want to hear the answer, I don't want you guys to think about it. What's coming towards us here, what's going away from us there, so everybody think about this a little bit. Sometimes it'd be helpful to draw out everything that's there. Okay, so let's start with this carbon here. If I rotate that bromide around, so the bromide is pointing up in that direction, Africa, what do you think? If that bromide is going that way, I'm going to rotate this around so that the bromide is in that direction. The methyl group is, so now we have to figure out if the bromide is there, what's coming towards us and what's going away from us. And again, you can always play with this sort of it's a sort of carousel, right? So if one was going one way, then everything else is moving around. So if the bromide moves up here, where's the proton going to move? here. Which means where's the methyl group going to move? Here, right? Okay, so let's do the same thing here. So we have our proton. It's not where we want it to be, right? The proton's going to swing down. So the proton's going to be there. If the proton is now here, the ethyl group is now here, correct? And I'll just make this methyl, methyl. The methyl group would be there. Now, when this elimination takes place, now a mistake that a lot of people make, and I saw this on the exam a lot, and so I'll just sort of reiterate this right now. That means nothing to me. Why does that mean nothing to me? Because it's not the geometry that an alkene has, right? You've got this group's coming in and out of the board, this one's coming up and down, right? It's a planar molecule. So you've either got to be, God, that's horrible. You either got to be in the same plane, in the sort of the XY plane, or one of the things that you may want to do here is you can have them both coming in and out of the board. So you can keep them in this plane or you can keep them in this plane, but you can't be somewhere in between, right? And so one of the reasons why I like this is I personally think it's easiest to see the chemistry in the plane of the board. And so here the chemistry is taking place in the plane of the board, which means that when I draw this, now this doesn't change, right? The proton is still coming towards you, and the methyl group is still going back. Here, the ethyl group is still coming towards you. The methyl group is still going back. So the methyl groups are on the same side, right? So this is this. Okay, so this is just sort of revisiting, just want to use this opportunity to revisit alkene stereochemistry. Now, one of the cool things about nitrogen being converted into a leaving group is it turns out that there's a couple different types of elimination that we can do with them. And it's not as simple. I like to teach it this way, and I'm just going to be completely upfront. There's problems with the way that I explain this because it only works in certain ways, but I do think that it's nice because you can at least in principle show complementary behaviors of stereoselectivity. So I'll try to be as real here as possible with you guys while still trying to make the broader point that I'm hoping to make. Okay, so in this case we had a bromide, and as it turns out, if you have, say for example, a nitrogen, so I'm going to keep this specific, and I'll explain why in a second. So I'm going to put a phenyl group there, yeah. That's NH2, thank you. It's going to be NH2, and just to make this easy, I'll keep everything in the plane of the board for now. And I'll stick with what we had before, a methyl and an ethyl group, okay? Now, we have learned a few different ways that we can convert nitrogen into a leaving group. If we were to convert this into nitrogen gas, N2, and we were to do an elimination of that, we're probably not going to, we're probably going to get stereochemistry comparable to what we would through an E1, right? Because it's going to leave rapidly, we're going to get more carbocation-like character to it. So for the sake of this elimination chemistry, let's not worry about nitrogen. Nitrogen's going to leave fairly quickly. But we did learn another less extreme leaving group from amines that we saw really when we first introduced this. And this is, Yes, so the quaternary amines, the quaternary salts, right? And so if we were to take this molecule and we were to treat it with bromomethane or iodomethane in excess, right? We sort of learned on the first day that if we treated this with an excess of bromomethane, right, what we will get to is is this salt here. And one of the special things about this salt, which complicates sort of the broader point that I want to make here, right? So these are all methyl groups. We were just talking about sterics before, right? In sort of first semester organic chemistry, we learned about how, for example, if you have a halogen, you can sort of eliminate sort of to generate the more substituted alkene, or you can basically eliminate to the less sterically accessible alkene, right? So we learned that the more sterically, the more substituted alkene is the more stable alkene, and so usually if we use a smaller base, that is the product that's going to form. If we use a bulkier base, we'll usually get the sort of the more sterically accessible proton to eliminate, and so we sort of learned this in these two ways. This is a very bulky leaving group. It's so bulky, in fact, that if you're given the option of multiple eliminations, multiple regioisomers, you will always go to the more sterically accessible sites. So you'll get the products that would ordinarily form from like potassium t-butoxide or something of that nature. So for these reasons, I chose to put a phenyl group there, so there was no way to eliminate at this position. So we can really only get one, and this is going to make my broader point. Given this option, if we were to treat this with a base, we would get the sort of the syn elimination product that we saw previously. Okay? And ultimately, the product that would form would be this molecule here, where we haven't really had to change anything. Again, this is going to equal the same as this. Right? So I've sort of drawn it already in the antiperiplanar fashion. One of the cool things about nitrogen is that you can actually convert nitrogen into a leaving group that won't go through this antiperiplanar elimination. It will actually go through what we call a syn elimination. And so it's complementary in nature in that from the same starting material in this case, you could actually choose which stereoisomer you might want to make. Okay? And the way that we would do that is, I'm not going to go through this specifically at this point, but actually I'll ask you guys. If we wanted to make the secondary amine, sort of revisiting what we were talking about earlier, if I wanted to not make the quaternary amine, but if I just wanted to stop with the secondary amine, how might I do that? Can I do it in one step? It might be tricky to do one step, right? So we might want to do two steps, right? You guys remember what we might want to do? Or at least in terms of what I kind of showed you guys as an option. A couple of reductive aminations, right? So you basically take formaldehyde, you make the imine, you reduce, you do the same thing again. That might be a way that this would work. But I'm trying to think if there's side products. I'm a little bit nervous that maybe there's some side products we might generate there because of this proton. But anyways, at least in principle, we might be able to do that. And what's cool here is that if you take this molecule and you oxidize it, okay, with an oxidant, I'm trying to think of the oxidant that they say in the book. They say MCPBA. I don't see the exact oxidant, but usually you can oxidize these to the N oxides with electrophilic oxidizing agents like MCPBA. Do you guys remember MCPBA? Did I do that right? MCPBA, I forget. But MCPBA is an electrophilic oxidant. Again, it's that sort of peroxy acid that we've sort of learned. You'll oxidize this nitrogen to the N oxide. And what's cool about this this. Is that this can actually, the fact that you have that N oxide in there, that N oxide, that O minus, can actually serve as the base, right? And so, and in principle, you can imagine it, sort of intermolecularly, but as goes with anything, if you can do something intramolecularly, usually that's going to be much faster, right? And so it turns out that this can undergo, when you take this and you make this and you heat it, what you can do is you can, you can rotate around 180 degrees, in which case everything's going to be eclipsing one another, but you're basically going to have this nitrogen and this proton being and when I rotate this around 180 degrees, my phenyl group and my proton, what's going to happen to the geometry of my phenyl group and my proton? It's going to, well, yeah, so exactly. When you rotate this around, the phenyl group is going 180 degrees as well, so it's going to be going back that way, bless you. The proton, again, is going to be coming from this way, right? So again, phenyl group back. Proton here, and should I find methyl groups there? And what can happen here is now we can do something called a syn elimination. Okay? These electrons can serve as the base, right? When that happens, these electrons can make the double bond, and will ultimately make the hydroxyl amines. Everybody see those electrons? Saw your headlight. So again, you'll notice there's sort of flow of electrons here, and we'll get the inverse stereochemistry. And so again, I think the broader point here that I'm trying to make is that, and I think it's worth sort of bringing up here, is that we've learned for the most part about sort of anti-periplanar eliminations, and that leads to one stereochemical outcome. But there is an alternative elimination that you can go through that is a syn elimination, and there's sort of the opposite ultimate stereochemical relationship between that two. Because in one case, again, you're anti-periplanar, and in the other case, you have to rotate around 180 degrees to get to the other one. So anyway, so that's the broader point that I want to make there. Certainly anticipate questions that could be related to knowing the stereochemistry one way or another. Mike, yeah?
When it comes to these eliminations, what if there's conformational ambiguity, like the most stable conformation?
When
Say you
there's
have two
conformational
protons, say you have two protons, and then you have the possibility of two eclipsing ones.
Good question.
Yes.
So, what do you guys think would happen? Let me ask that question. If, for example, this was not a methyl group, but this were a proton. We could end up with ultimately, so our methyl group would be our proton. And so we'll label these as HA and HB. HA, and this will be HB. And so this is ultimately, the trans product is the product that would arise from HA. But Mike's question is, well, there's another proton there. You could also rotate around and have the other proton be at that position. And the quick answer is, yes, you would go to the more conformationally stable product, but let's ask the question of why. And the reason is that when you compare, if we rotate this around such that HB is down, right, let's just do this again. So if HB is down, the ethyl group's going to be now coming towards you guys. And the HA is going up. same reason, so if we made this Me3 plus phenyl proton, this would lead to phenyl. Does everybody see that? So if we rotate around and have the HB do the elimination, that's going to lead to the opposite stereochemistry. Does everybody see that? What? Yeah? Mike was asking about the potential situation where you've got multiple protons. We've got HA and HB. We have to go through antiplanar behavior, but we could have HA be the antiperiplanar proton, or we could have the HB be the antiperiplanar proton, right? Those two, whichever one that we choose, will lead to the more stable, will lead to different products. So when we do one, it's going to go to trans, we do the other, it's going to be cis. And the answer is ultimately that it's going to go to the more stable one, but the reason, you can argue thermodynamics, but in principle it's also a kinetic reason as well, right? If you draw the Newman projection of this versus the Newman projection of this, you're going to see that this one, maybe this is something you guys can do in your off time now, but you'll see that this has a higher energy, this has a lower energy configuration than this one as well. So more stable. So this one is more stable, right? And so since it's more stable, it takes lower energy to get to that. So there's going to be a higher population of that, which means that that's going to be more likely one to form. So good question. And that served the last 5 minutes. So again, watch, if you didn't hear earlier, and I'll try to get this video up, but watch before next class, make sure that you watch the CC bond forming. It is now. I sent you guys a Blackboard thing as well. It's not working? Okay, I'll check it out as soon as I get up. But if you go to actually the CC bond forming down lower on my website, the CC bond forming link should still be on my website. So if you find the CC, and there should be a couple classes, so if one's not working, maybe check the other one. But refresh again, what you want to know about is carbon-carbon coupling, so Suzuki, Heck, Stille, and then also metathesis. And so familiarize yourself with those before next class.